Hello there. How are you? I hope you are doing okay, and maybe you got to get outside today, or maybe will tomorrow get some sunshine. When you're out there, listen for the birds. I heard a bunch of red-winged blackbirds, and you might hear my guinea fowl actually right now. And those red-winged blackbirds are a signal that spring is coming. Actually, Thursday, towards like 11:49 p.m. is the vernal equinox, and then Friday is the first full day of spring. Um, and these sounds, these bird calls that you hear, are complex combinations of frequencies. And so when I'm out and I hear a bird call that I don't know, I use this app that I have called BirdNet. And what that does is it takes frequency and amplitude data with time and allows me to kind of select it, and it will compare this frequency and amplitude data to Cornell Lab of Ornithology's uh, database of bird sounds. So I'll show you what I mean by that. So this is a spectrogram of a red-winged blackbird call. So we can see frequency in kilohertz on the y-axis, time on the x-axis, and it has a very distinctive signature with time where it drops the frequency. And then there's these different harmonics or different notes that it makes, and one is louder than the other. And if you haven't checked out the Cornell Lab of Ornithology's bird identification catalog and app called Merlin, definitely do that too if you're looking for something cool to do. So I want us to look at these notes that we can make, these kind of pure notes, even though birds and us, we make layered sounds of multiple notes, which you can decompose with something called Fourier analysis, but that's some complex math for another day. But we want to look at pure notes, and we looked at that starting on Friday, and I just wanted to revisit that with the idea of resonance. So we looked at resonance and standing waves, which are kind of the same thing, in strings. And if you want to take notes on this, you can. I am going to export this as a PDF and attach it to Schoology as well. So if we have a string that's fixed at both ends, my husband let me borrow his guitar, kind of like this awesome guitar. If we put energy into the string, it has a fundamental frequency. And that frequency is the frequency that it makes sound at. And we can identify the multiple frequencies that we can make on a string by their harmonics. And this is our first dabble into the idea of what's called quantization, which is the foundation of quantum mechanics. Note the prefix quant, like quantity or quantitative, which refers to the idea of a specific amount. So instead of there being an infinite number of waves that cause the string to resonate, there are just few specific waves that cause the string to resonate. And actually, when my dog was in here making noise like he likes to do, the guitar was resonating with one of the noises or pitches that my dog was making noise at. So these are discrete, specific numbers of, in our case, in the case of a string that's fixed at both ends, half wavelengths that can fit in the length of the string. So the harmonic number is the number of half wavelengths that fit in the string, or the number of fundamentals. And in this case, the fundamental is a half of a wave. So the length of the string has a half of a wave, and so the wavelength of that first harmonic is 2 times L. So we can identify each harmonic by this integer number n, which corresponds to how many half wavelengths or how many of the fundamental fit in the length of the string. And we can come up with a generalized expression. So the wavelength of any harmonic n is equal to 2 times the length of 2 divided by n, or rather 2 times the length of the string divided by n, where n is any integer, any non-zero positive integer. We can do the same thing for open-ended pipes. So an example of an open-ended pipe would be like a wind chime, where I have this boom whacker here that will analyze. And the symmetry that exists in the strings, where you have kind of the same thing at both ends, a node here, here, and a node here, you see in the open-ended pipe. So we actually see the same pattern when it comes to expressing the wavelength of different harmonics. We have an antinode at each open end, so the fundamental can be seen when we have a half of a wave fitting into the length of the tube. And this is actually a lab that we would have done yesterday, I guess. And it would have been very noisy, and I will just demonstrate it to you with a frequency generator that I have on my phone. So we're looking for the fundamental, or basically a frequency that makes this thing get really loud, kind of like annoyingly loud. And so we can do some math with that, or we can just kind of play around, and I would have let you do whatever you wanted there, but I'll show you both ways. So right now I'm at 229 hertz, and I can increase the frequency. And it's not really that loud right now, but as I get closer to the fundamental, you can hear it start to get really loud. So it was right around 345, something like that. That seemed to be the most annoying or loud noise. So I'm guessing that that is the fundamental frequency. So we can do the math on that, right? So I can measure the length of my tube. I have my handy dandy at-home meter stick here. So the length of the tube is about 46.5 centimeters. So the wavelength of the fundamental harmonic is 2 times 46.5 centimeters. And so the frequency of the fundamental harmonic should be the speed of sound in this room, which if it's room temperature-ish is 343. So the frequency is V over lambda, and we're finding the first one. So 343 meters per second, that's a little chilly. And 2 times the length of the tube, which is 0.465 meters. And so when I do that math, I get 363 hertz. And when I just made that sound, we found the harmonic at about 345 hertz. So there's a little measurement error there, potentially. So what's cool about this is the second harmonic is just double the first harmonic, or is 2 times the first. The third is 3 times the first, the frequency of it, and the fourth is 4 times the first. So I can predict the second harmonic by multiplying either the frequency I calculated or the frequency I found by 2. So if I multiply the frequency I found by 2, which is 345, I get 690. So let's look for that second most annoying sound around 690 hertz. So that seemed to be around 685 hertz. So those are some examples of different harmonics in tubes that are open at both ends. We've got this really nice symmetry happening here. And so we have the same expressions for wavelength and frequency that we did with the similar symmetry in strings. Pause here for a second because there's an error in what I had written down here. And the pattern of harmonics in an open-ended tube is the same as a pattern of harmonics in a string that's fixed at both ends, because they both have that same symmetry. They have to have the same thing happening at both ends. So the wavelength for any n harmonic or overtone is 2L divided by n, and the frequency for any n harmonic or overtone is the speed times the harmonic number divided by 2 times L. And we have harmonics that are nice, positive non-zero integers. Now, pipes that are open at one end but closed at the other end have a very different symmetry. They don't have symmetry, really. They have a node at one end and an antinode at the other, so the geometry is pretty different. I have this bottle here. So this would be an example of pipe that's closed at one end, open at another end. Similar to your classic singing wine glass, and I have just an example of a guy playing Hallelujah. So these are some pretty cool examples. So let's analyze this geometry, because it is indeed different. So what we have here is a quarter wavelength fitting into our tube, and so the wavelength of the fundamental is 4 times the length of the tube if we call this one the fundamental. So then the frequency, of course, would be V over the wavelength. And what's a little weird is, while before the harmonic number was the number of fundamentals that fit in the tube, so like there's 2 half wavelengths in our second harmonic. If I had 2 of the fundamentals here, then I wouldn't have, that can't actually be created when we have one open end and one closed end. So what we have for the next overtone that we hear is 3 of the fundamentals fitting inside the tube. So we can call this one, if we think about it, the n equals 3 standing wave that fits in the tube. And the n equals 2 does not exist. So n must be odd in this case if we're looking at these patterns. You don't always have to look at these patterns. You can always draw it and figure it out, but I think the patterns are cool, and I'm happy to show you them. So we have 3/4 of a wavelength fitting in there, and so I would need 4/3 of the length L in order to get a whole wave, because I don't have the whole wave. And so the frequency of this would be 3V over 4L. And if we look at the next overtone, we can see that 5 fundamentals, 5/4 wavelengths fit in. So we would need 4/5 of the tube, because we have a whole one right here. So 4/5 of the tube make a wavelength, and the frequency of that is 5V over 4L. So if we were to come up with a generalized expression for any wavelength of a overtone or harmonic in a tube that is open at one end and closed at another end, we could just say 4L over n. And Fn would be n times V over 4L, where n must be an odd integer. So this is just a comparison of the two kind of side by side. We can see that the pipe that's open at both ends is very symmetric, where the pipe that is open at one end has kind of this odd symmetry, which results in us having to look at just odd integer numbers if we're coming up with a generalized expression for the frequency. And again, you don't need to have these memorized. You can always draw the picture and look at the geometry to figure it out. So we can visualize sound waves in cool ways, and I just want to check in and show you a couple different things. So this is a sound wave with a pipe that I believe is open at both ends, and there's methane gas in here that he's lit on fire and playing a note in it. You change the note,
this video is sponsored by
you can change the wavelength of the wave. And I'll put those video links in the comments, but I'm trying to keep this short. This was a picture of the board that was there on Friday. And we can look at some example problems. So why does a clarinet play a lower note than a flute if both instruments are about the same length? Feel free to pause and consider this question. The flute is open at both ends, whereas the clarinet, with your mouth over the top of it, is closed at one end. They act differently and have different harmonics. So with the flute, you can produce a higher frequency note, which is a shorter wavelength, and with the clarinet, it has to have a longer wavelength because only that like quarter wave fits in the fundamental of the clarinet. What length should a pipe open at both ends have to be to produce a fundamental frequency of 110 hertz? So if the frequency is 110 hertz, the speed of sound is 343 meters per second. We're dealing with a pipe that's open at both ends. And so if we're interested in the fundamental frequency, we have an antinode at each end, and they're like opposite. So it's a crest to a valley. So we're interested in the length of this pipe. And so for the fundamental, the wavelength is equal to 2 times the length. And so if V equals F lambda, 343 equals 110 times 2 times the length. So we'll just take, so L equals 343 divided by 220. And I'll just do that math real fast. So that's 1.56 meters. So there's some problems in your homework that are similar to these. Now we're looking at really simple cases in a couple dimensions, and there's really cool cases in more dimensions that I would love to show you real quick. And if you're interested in learning more and have the time, you should definitely explore these. So this is when a metal plate is being driven up and down at its resonant frequency and then different harmonics, and we can see that the sand, this white stuff or salt, stays at the nodes. And at the antinodes, there's so much constructive interference, it's bouncing up and down. The sand has to move to a point of destructive interference where there is no movement of this very flimsy metal plate. As we increase the frequency and get to higher harmonics, we see the patterns get more and more complex, which is really cool. And then this has consequences with sound, which actually will allow you, if you align speakers in interesting arrangements, you can manipulate objects and make them float midair with sound waves. Notice this is styrofoam. It's not like we're levitating a person here. They do some other larger objects, like a little LED, little piece of wood, I don't know what that is, little matchstick, screw, a nut. So these are hanging out in those nodes. So I hope this was helpful. I'll see you in office hours if you have questions on your homework or anything we talked about here. See the links below for the cool videos I featured and Schoology for a PDF of the notes. Have a good day.